Okay, dear students, today we will discuss pattern matching algorithms. Um, so, starting with what is pattern matching and the different, widely known and used pattern matching algorithm for academic purpose, we'll discuss today. What do you mean by pattern matching? If you are trying to search for a pattern in a given string, rather, right? Um, you have a string of t, let us say, in which you want to search for a particular pattern p. P is always a substring of your text. Like for example, your t text is the rain in Spain stays mainly on the plain, in which you want to search for a pattern like let us say nth. It is available somewhere over here, rather, right? So searching for such kind of thing is what exactly. And what are the applications of pattern matching? Text editors. In text editors, how do you search with the help of Control F? You'll get a pop-up window where you can probably say type your keyword or a pattern which you are rather looking for it, because your text or your MS file, MS Word file rather, could be of 100 pages or could be 200 pages, but then you want to search for a particular word out of it. With Word, you can probably extract that respective text which is associated with that, rather. So just press Control F with the help of a keyword. You press in that particular pop up after you press Control F, you can be able to search. So this is an application of pattern matching itself, right? For example, if you go for web search engines like Google, how you are able to search for a document. There are a lot of documents which are rather available across which, with the help of a keyword, you are able to search respective, uh, you know, very relevant, files from that big repository. So very vast applications rather, of this pattern matching you can find in even image analysis also, when you are searching for a particular part of in a very big image, rather, right? So these are all some of the applications of pattern matching. Starting with the brute force, as I said. There are about a couple of algorithms that we're going to see probably: brute force, Bayermore, and Nuthmar Pratt. But before we move on to these algorithms, we'll see some of the terminology that is being used here across these algorithms, right? So, a substring s of I to j, right, is a string fragment that you can say starting with an index I to j. If I have any substring represented as of I to j, is going to represent with the indexes from I to j is nothing but a substring over that particular string s, rather, right? So what do you mean by prefix? Basically, prefix starts with zero always, right? And to any I in the given string is a prefix, rather, right? If you have, um, for example, you have, let us say, my name. My name is a string in which what are the prefixes? You say m is a prefix, my is a prefix, my n is a prefix, my n a is a prefix, my na my num is a prefix. Yes or no? These are all the prefixes, you can say, rather, right? So similarly, what do you mean by suffix? Basically, suffix, start with certain I, but then end with the last character. End with the last character, right? It should end with the last character. It means simple E is a suffix of my name. You can say EM is also a suffix of this my name, or you can say AME is also a suffix of this my name, or NAME is also a suffix of this particular my name. Yes or no? And Y name. Yes or no? So these are some of the suffixes will always have the last character. So the last character of the string. Fine. So you can have a good number of suffixes to be derived from a single string like this, where the condition is the last character of the string must be there. You can see last character of the string is E, right? E is available in all the suffixes. So these are all the suffixes of your my name, I can say, rather, right? And the name itself, fine. And when I say prefix should have always the first character, right, of the string. So first character of this particular string M. So M is a prefix, mine is a prefix, of course, mina is a prefix. These are all the prefixes, right? So I is any index that could be from 0 to, as I said, m minus 1. It means 0 to 0. So simple mem is a prefix in this case, right? Similarly, in suffix, when I is m minus 1, the last character, like, just E could also be a suffix, right? And when I is 0, the suffix, the complete name itself is also a suffix, right? And the complete name is also a prefix of the same. Name itself is a prefix and suffix, both of course, but then the other prefixes and suffixes that can be, derived from this particular, name is, these are all the prefixes and these are all the suffixes, right, of this particular my name. I hope you understand what do you mean by prefix and what do you mean by suffix. The condition for prefix is the first character of that particular string must be there, and in suffix, last character must be there. This is the condition, right? So these are some of the terminology that I'm going to use here across these algorithms, right? So if you look at substring, the string is given Andrew. Andrew is the author name who has rather prepared this particular PPT from where I've taken. So Andrew, Andrew, right? So you can see here this is a string given. From this particular string, if I probably derive certain characters to form a substring like NDR, is a substring, right? Starting from 1 to 3. If the indexes are starting with 0, this is 1, this is 2, this is 3, this is 4. So indexes starting with 1 to 3 will form a substring of this particular string, right? All possible prefixes. What could be all possible prefixes of this particular Andrew? Say, Andrew name itself is, as I said, right? Remove the last character under A-N-D-R-E or A-N-D-R, A-N-D, and A. Like I have explained it with my name, rather, right? Similarly, what are the suffixes of S of the same? If you say the name itself, as I said, right, it is also a suffix, but then leaving the first character, remove the first character, because the condition for suffixes is last character must be there. You can see in all the suffixes, last character is there or not? Yes. And probably if you can see here, in the prefixes of all this of Andrew, you can see there is a first character. Do you find the first character? Yes, there is a first character available. So this is the condition for prefix. Prefix should have always the first character of the string, and the suffixes will have the last character of the string. The name itself is of course a prefix and suffix of the same, but then you can probably generate any number of prefixes by removing the last character and from there onward subsequent until you reach the first character to be left. Similarly, to generate the suffixes starting from the string itself by removing the first character and then subsequently the next character until the last character is left. So these are all the suffixes that you can probably generate and prefixes you can generate from this particular angle. Anyway, coming to the brute force algorithm, this is the first, and widely known algorithm used. Is a very simple algorithm as well. The other way around, we can say, to find the pattern matching, technique. Let us look at this particular text. You have Andrew text in which I want to look for a pattern called REW, right? So in brute force, how exactly you do is you start with the first character of the pattern with the first character of the text, right? So you can see here you have taken the first character of the text and you have taken the first character of the pattern. You have compared. There is no match. Fine. If there is no match, then what you do? You will move the pattern right by one position so that the next character of the text can be compared with the first character of your pattern, rather, right? And you compare. When there is no match, then again you will shift the pattern right by one position in order to align with the next character of the text, so that you can start comparing your pattern characters from the next character of the text with the first character of your pattern rather, right? So every time what is happening, P is moving uh, one character at a time, right? Throw T. Fine. So this is what the logic behind the brute force. You can see here the program is written in Java. So brute force technique, you can see here, we have taken a for loop here. There are two iterators I and j. We are using, of course, I and j both we are using in order to locate the positions of the text and the pattern rather, right? So here j is starting with 0, which is being used here in order to locate the positions of your pattern, and I is initially 0, so I plus j, because I will take an increment in order to align the pattern when there is a mismatch with the next character of the text. I gets incremented, right? Whenever there is a mismatch, what is happening here, you go for the next iteration, right? When there is a mismatch, what is happening? When there is a match, then you increment j. You increment j. When you increment j, both the positions of the text and going to be and the pattern are going to be incremented, because here you can see in text the index is been incremented with j here, right? I is been incremented with j, and when you increment j value, automatically the index position of the text also get incremented in addition to your pattern rather, right, which is being here identified with the help of j. But when there is a mismatch, what happens? When there is a mismatch, you go for the next iteration, right? When there is a mismatch, you need to align the pattern to the next character of your text. So by incrementing I, what happens? Automatically, the text will take on to the next character of the the next character to itself, so that pattern again will start with 0. Pattern again starting with 0, because you are taking j value to indicate the positions of the pattern, which always starts with 0 for every iteration of the loop. So, but then since here text is being starting with I value with an increment of j. So when j is 0, obviously text is going to be text position is going to be from the next character, right? Where there was a mismatch rather, right? So that way you are able to compare. When there is a match, then j is going to be incremented, and then this while loop is going to be repeated. If there is a match, how long? Until j less than m, right? When j equal to m, then you come out of it, and then you return the position of I, where from where you could able to found that respective pattern in that particular given string. This is the algorithm which is rather available for us, right? So we can implement the same in the main as well. You can just create here you can see we are calling that particular brute force function by passing the strings that we are going to give as arguments during the command line rather, right? First is the text and another one is the pattern, right? Anyway, so this is the program of Java that you can rather rewrite in C++ as well. As part of your lab, I have given in C++ anyway, right? Now, if you look at the time complexity of brute force, it is going to be mn in the worst case, right? In the worst case, it's going to be mn. But most of the searches in ordinary for ordinary text, it is m plus n, right? And if you look at by analyzing what we could able to understand, that the brute force algorithm is fast when the alphabets of the text is a large, like when you have alphabets including uppercase, lowercase, and digits and all. But it is very slower when the alphabet is very small. Like for example, binary files, if you have like 0 and 1 kind of thing, right? Example of a worst case. For example, you have a text like this, where you can see all little characters of this particular text are a, only the last is h. Now out of it you want to search for just a, so you have to start with the first character position of the text, being compared with the first character of the pattern. There is a match, there is a match, there is a match, there is a mismatch. When there is a mismatch, what do? You just advance this and then compare it from here again. See what is happening as part of our algorithm. When there is a mismatch at any position across our pattern, the next character from where the next iteration, when the next iteration comes, of course, right, the text in text, the position you are taking is the just next character rather, right? So again you start from here, then what happens again, this a is going to be compared with this a, and here there is a mismatch. Then just you are advancing it for one position. So how long you going to do this? See, there are three comparisons. Every time is going to be wasted rather, right? Only after three comparisons you are coming to know that there is a mismatch. But then how many character advancements you are doing in text in order to align your pattern to go for the next iteration to start comparing rather. It is just one character, right? So if you have about, say, how many characters, if you can count it, say for example 20 characters you have, after which you have h, then for every mismatch there are how many comparisons you are going to simply waste is around four comparisons you're going to waste, right? So it's almost like, if you have m characters, this is about 21 characters, right? And how many pattern characters you have, for example, four characters. So how many times you are going to make the comparison is going to be 21 into 4, I can say, right? M into n, yes or no? This is the worst case scenario that you can probably find here. Yes. But if the characters are, if the alphabet set is huge, then obviously you can see the time complexity will be reduced from mn to m plus n. Fine. For example, the next example in which you have a text like a string searching example is standard, wherein you have to search for store, right? There is a mismatch at the beginning itself. So you need to do the further searches. Only then you need to make an alignment. Like how here, what is happening after only four comparison, last comparison. After you compare all the characters of the pattern, you are able to decide that there is a mismatch and you have to go for the next iteration rather, right? So here, but in this particular example where you can see for the first character itself there is a mismatch, so you take an advancement, and probably I will be here, and then this is going to be compared with this. There is a mismatch, so then probably is going to be compared with this, right? So like this. That way you can see the number of comparisons from mn to it can be reduced to less, which can be in average case around m plus n. Okay. But then our effort here putting towards reducing the time complexity. In order to reduce the time complexity, you need to change the algorithm. You need to make the algorithm such a way that it can intelligibly compare the characters and then could able to give us a result in a shorter time. So in that line itself, we are moving towards some of the subsequent algorithms. One of which we are here looking at the Bayer-Moore algorithm. So in Bayer-Moore algorithm, there are two techniques we are using. One is the looking glass technique. Another one is the character jump technique, right? So in looking glass technique, if you can see, what happens is you are going to compare the characters from the backwards instead of forward. Like how in brute force we were, comparing the characters from the first character of the pattern with the first character of the test. But whereas here from the backward we are trying to, compare the characters. It means the last character of your pattern, when being aligned with the number of characters required with the text, that text character is going to be compared rather, right? So that way, by aligning your pattern with the text, the last character of your pattern with the corresponding character of your text is going to be compared. If there is a match, then with a decrement, you move in a backward direction until you reach the first character of your pattern. And if all the characters get matched, then probably you will return the position of the text from where actually that particular pattern could have been retrieved. So first thing is backward technique you are using. The second thing that you are here using is the character jump technique. Character jump here you're going to use whenever there is a mismatch, right? Whenever there is a mismatch at certain character X, what is that you're going to do? You are intelligibly shifting, the positions across both the text and pattern in order to align and see that the number of comparisons can be reduced in order to find the respective pattern in your text rather, right? So, like how exactly when there is a mismatch occurs, you're aligning this pattern with the text is with there are three possible situations or cases that you are going to adopt, right? So one of such case, like here in this particular case, you can see if there is a mismatch occur. As I said, you are going to compare from the backward, right? So initially your J was here, right? Your J was here, and your A was here somewhere, right? So uh, now after you have compared, when you have got a match, then you have decremented. So I is here, now J is here. You can see there is a mismatch, right? So when there is a mismatch like this, what happens? What you do is you're going to shift P. This pattern is going to be shifted to right, right? You're shifting this pattern right to align the last occurrence of X in P. What is the last occurrence of that X? X is the character of T at which you got a mismatch, rather, right? Remember, X is the character at which you got a mismatch, right? X is the character of text at which you got a mismatch, right? So when you get a mismatch at certain character X of text, what is that you are going to do is you are going to shift P to the right to align the last occurrence of X in P. Last occurrence of X in P is somewhere here, right? Yes or no? So you are going to align this character with this X. It means you are shifting this pattern P to write such a way that where the last occurrence of X in P will be aligned with the X in text T. Got it? So you can see here, this X when get aligned with the position at which the mismatch occur at T, you got like this, right? Then your new J starts here. Always you start comparing it from the last character onwards, last character of the pattern, right? Because we are using backward technique. That is for standard rather, right? And the second thing that probably we are going to discuss as part of these three different cases, rather, right? So now your new J will be here, and obviously your new I will be somewhere here, right? Because when you are aligning the last occurrence of X in P with T of I was here, right? Now with TF5, when you have done it, then obviously when J is going to be disturbed, rather, right? J will be the last character of your pattern again. So somewhere here it was J before, but now it's going to be the last character. Again, you have to start doing that respect to next iteration, right? So when your new J is somewhere here, then your new I will be here, right? In correspondence to your J, I will be somewhere here when you have aligned this character, right, of last occurrence of X with T of I, right? So this occurrence is going to be identified with another function. Of course, we'll do that. Probably we'll see how this last occurrence function will help us out in identifying the positions to be aligned in both text and pattern. Now coming to case 2. In case 2, uh, when there is a mismatch, right, at somewhere X, but a shift right to the last occurrence is not possible. Like, for example, you have started comparing your text, initially your J is here, your I is here, you compared and it was matched, and you decrement I is here and J is here, there's a match. So you decrement I is here, now J is here, there is a mismatch. Now, after you identified that there is a mismatch at X, some X, right? What is the last occurrence of X in P? It is not before J, right? It is after j, the other way around, you can see, right? So to it is not possible to align this x by shifting right. We have to only do the right shifting right position. I can't go with the shift left, rather, right? I have to do only the shift right. So it is not possible for me to align this occurrence, that is X, okay, the occurrence of this mismatch character here in P by shifting right. It is not possible here. So in this situation, what is that you do is you are going to shift P right by one character to T of I plus one, right? I is here, I is here, right? And what is I plus 1? I plus 1 is here, right? So to I plus 1, you will shift, right? So when you shift I plus 1, it is nothing but you are shifting P right by one position. See, P was here, in correspondence with G. Now, when you are shifting to Ti plus 1, where J is exactly, then it means that you are shifting P right by one position on the whole. Then again, J and U starts from the last character of your pattern. Then correspondingly, I will also will be changed with a new position in T. Again, you start comparing both I and J, and the next iteration is going to be rather continued like this. Coming to case 3, if case 1 and case 2 do not apply, it means that you when there is a mismatch for a particular character, that character is not at all available, okay, is not at all available. If there is available, if that character is available, and the last occurrence of the same is to align with to align with is possible by shifting the pattern right, then we go with case 1. But let us say that last occurrence of x is to align with text is not possible by shifting pattern right by pattern right, then we will just shift pattern right by one character to align with ti plus 1. This is case 2. In case 3, what is that you are going to do here is, when both of these cases does not apply, it means the character of T where you got a mismatch is not at all available in pattern. Then what do you do here is you will shift the P to align P of 0 to T of I plus 1. P of 0, it means you are shifting completely the entire pattern, you are shifting towards right, so that P of 0 will be aligned with T of I plus 1, right? This is I plus 1. I was here, I was at X. Now I plus 1 obviously is A, right? So to align P of 0 with I plus 1, how many right shifts are required? You'll be doing that. It means you are shifting the P, entire P to the right in order to align P of 0 with T of I plus 1. Then you can probably again, your J starts with the last character. So obviously I will also be changed. Your J new and your I new are available with you once you make this right, shift to align with P of 0 with T of I plus 1. Again, you start doing the next iteration. Next iteration is comparing the character of text positioned with I, and character of pattern positioned with J. If there is a match, then you decrease, and then you go like that until you reach the first character of the pattern. If all the characters get matched, then you will retrieve the position of I from where the pattern could have been found in that particular text, right? So these are the three extreme possible cases we are adopting to jump the character. Fine. Now let us look at this example to understand the same. A pattern matching algorithm is the text you are given, right? So this is the text is given, and rhythm, RITHM, rhythm is the pattern to be identified, is required to be searched in this. So what exactly you do? Your J is here and your I is here. You compare, you know, T of I with P of I. There is a mismatch. When there is a mismatch, you go with first see that whether you fall with case 1 or case 2 or case 3. What is the case 1? In case 1, you will look for this particular mismatch character T, is it available in the pattern? Yes, it is available. If it is available, is it possible to align that character by shifting pattern to right? Yes, it is possible. It means it is coming under case 1. Understand, this is case 1. Okay, so under case 1, what is that you do? You align this character, last occurrence of your T, that is T here, with the character, with T of I, with T of I, right? So you can see here, you're aligning this T. Once you align this T, what happens? Your J is somewhere here, and the corresponding position in text is I here, right? Again, you start comparing this T of I with P of J. There is a mismatch. Now, when there is a mismatch, you can see the character at which you got a mismatch is E. Do you have this E here? No, you don't have at all. If you don't have that, then you will come under case 3. Understand? You will come under case 3. So in case 3, what do? You will shift the entire pattern to align P of 0. This is your P of 0, right? P of 0 with T of I plus 1. T of I plus 1 is this, right? So you will align this. Yes or no? So then your J becomes, your new j will point to m, your new I will point to this. Again you compare. When you compare, you can say there is a mismatch. Again, this is case 3. Yes or no? When there is a case 3, again what do? You have to shift this entire pattern to align P of 0 with T of I plus 1. Your I was somewhere here. Now I plus 1 is this. So you can see here, by aligning this. Now your J, new J is this, and your new I is this. Again you are comparing. You can see there is a mismatch. And do you have N here? No. So it again comes under case 3. So under case 3, what do? This is the fourth iteration, right? So under case 3, what do? You shift the entire pattern to right in order to align P of 0 with T of I plus 1, right? So this is your P of 0 and this is your T of I plus 1. Yes or no? Okay. So then your J, new J becomes this, right? Your new J is this, your new I is this. Again, you start comparing your, P of I with P of J in the next iteration. In fifth iteration, you got a mismatch. Again, there is a mismatch, you can see, right? So do you have this character which is mismatched in text is available in your pattern? It is not available. So it is again under case 3. So under case 3, what do? You have to shift the entire pattern to write in order to align P of 0. P of 0 is this, right? P of 0 with T of I plus 1. I is here, T of I plus 1. T of I plus 1 is this, right? So when you align this, your new J will be here and your new I will be here. Again, when you compare, you can see there is a mismatch, and the character of text which is mismatch is not at all is available. Yes, it's available. You can see it is available. If it is available, then what you do? The last occurrence of this character is here in this string. Is it possible to shift this particular pattern to right by one position, pattern to right in order to align this last occurrence with T of I? Yes, it is possible. Yes, it is possible. So what happens? You align this particular H, right? That is last occurrence of H is here, right? You align this H with T of I by shifting pattern to right, and now your j, new j becomes this, right? And your new I becomes this, and you compare the characters of text and pattern with I and j indices respectively. You got a match, then you decrement both I and j, and you got a match, you got a match here, you got a match, you got a match. So when j is 0, of course, right? So further you can't do it, right? So when j is 0, of course you stop doing it, and then you will return the position of this I at which your pattern is being identified, right? So this is what exactly the algorithm is. So you can see here, what is that you do? You first have to find the last occurrence. For example, your pattern is given. So while designing the algorithm, you can see here, this is a pattern A, B, A, C, A, B. So for all this alphabets, actually the alphabet set is also given. Alphabet set is, it means your text can carry how many characters? A B C D. A B C D repeatedly it can carry, right? So this is the alphabet set of the text given, and this is the pattern, right? So in order to identify this pattern with the text having these alphabet set, first you need to identify the first you need to construct the last occurrence table. So this is your last occurrence table you have constructed here. See how many characters you have? A B C D. For all A B C D, what could be the last occurrence function that is determined through this particular pattern, right? For A, when the last A is occurred in this particular pattern, you can see here, right? That is position 4. So this is how you are going to calculate the last occurrence value of the alphabet set. Next alphabet in the alphabet set is B. So for B, what is the last occurrence of last occurrence for the pattern? That is 5. So it is 5. Then for C it is 3. So for D, if you do not have that particular character in the pattern, yes, your alphabet set carries 4 characters A, B, C, D, but your pattern may not carry all those. Your text may carry, but your pattern may not carry all the alphabets. Like for example, this particular character D, the pattern is not carrying. Then the last occurrence value will be -1. Okay, this is how you calculate the last occurrence table. Fine. Here, with the help of an array, we are going to implement this in Barmore algorithm. There is another example is given. You can see here, if you if the text is given like this, and the alphabet set is A B C D. The alphabet set is given as A B C D. Right. First, you need to calculate the last occurrence table for the given pattern. This is your given pattern. So when A is being occurred lastly, it is 0, 1, 2, 3, 4. So 4, B is 5, C is 3, D is -1 with the pattern that is discussed before. Now you want to search for this particular pattern in this particular given text. So how do you do that? You start with J here, I here, compare, there is a mismatch, and then when there is a mismatch, you will see that under which particular case you fall with. The mismatch character is A, whose last occurrence value is 4. Fine. So that will tell us where to advance, right? So you can see the algorithm from algorithm point of view. You can see here. So bar match, you can see by build loss is the function by passing the pattern entire pattern. We are calculating the last occurrences value with the help of an array, and we are storing in the same. Then we are finding the length of both text and pattern, and they are here represented with n and m variables, and I is starting with m minus 1. I also required to start with m minus 1, right? Initially, when you align, since the comparison is from the backward onwards, so I also should be aligned with the last character position of your pattern. Pattern consisting of how many characters? M. So then obviously J, if I am using to point to pattern, then J starting with m minus 1. Obviously, I also should start with m minus 1. Okay. So you can see here, you compare the character of the pattern position with J and position with I in text correspondingly. When there is a match, then obviously what do? You keep on repeating this by decrementing, right? By decrementing I value and G value, and once you reaches J value is 0, you return the I. This is what exactly your algorithm. But when there is a mismatch, right? When there is a mismatch, then you have to calculate the last occurrence value. So last occurrence is already we have I calculated with the help of a function, and which is stored in last array. So just send that particular I the character of text where you got the mismatch, right? The character of the text where you got mismatch is text dot character at I. So which if you send to this particular last array, it will give us the last occurrence value of the same that we have calculated here with the help of this table, you can see, right? So that last occurrence value will help us to align both j and I in all three cases, right? J will start with m minus 1 anyway, right? Because when there is a mismatch, always again for the next iteration, the characters from pattern you start from the last itself. So J is the position to start the characters to compare from the pattern. So it has to start with m minus 1 anyway. But I is where you are going to have a kind of logic to be applied, because adopting all these three cases. See, all these three cases are going to be here, solved with this particular formula. See, what we are doing is we are taking j and 1 plus LO is the last occurrence value from the table, right? From the table, 1 plus LO and the j value. Whichever is minimum out of it, we'll take that and we'll subtract it from the sum of I plus L. That will give us the I value in order to align our pattern when we fall under all three possible cases, rather, right? Fine, you can probably trace this algorithm, and then you probably understand better with that particular text and pattern I have given. See, this is the last occurrence function here to calculate all the last occurrences value. See, we have actually taken 128 array. Actually, this last array is in size of 128, because ASCII characters consists of how many 128 ASCII characters you have, rather, right? So this particular for loop is initially initializing the entire last array. This last array consists of how many elements? 128 elements. All these 128 elements initially minus 1. But then your alphabet set does not carry the entire ASCII set, right? It as per the example that I have taken here, wherein you can see there are only four characters, right? A, B, C, D is your alphabet set. So only for that you need to calculate. So that is what exactly you are trying to do here, passing this entire pattern characters you are passing as an index to this last. So when you are passing the pattern characters, your pattern carries A B something like this, right? You have the pattern characters A B A C A B, right? You have something like this: A B A C A B. So when A is passed here, what is the ASCII equivalent value of A? It is small a. Small a is 94, something like that. Okay. So at 94, what happens? That I value is from this I value is this is 0, 1, 2, 3, 4, and 5, right? So I value will be stored. So for at last of 95, I'm showing for one. 94 initially it will be 0, right? And then for the next iteration what happens, you will get the b value is 95, right? So last of 95 is going to be 1 here initially, right? I value will be stored at that respective corresponding index of the class style, rather, right? Then again, for the next iteration what happens, you got a value 2, so this 94 get overridden with 2 here, right? Again, when it is repeated for the next iteration, what happens? For C is 95, right? Last of 95, and 95 equal to what? 3, right? So similarly, again you got for A. So A value will be replaced with 4 now, you can see, right? Now for B again when replaced it will be 5. So you can see you got the last occurrence values for A it is 4, yes or no? For B it is 5. For C it is 3. And for D, of course, it remains minus 1 only, because for all other characters it is minus 1. No, that was done before itself. That's how you are calculating this last occurrence array, with the help of this particular function. And this particular formula, as I said, will help you to adopt all these three cases, right? You can test it with certain iterations. You will understand it better. I hope this is clear to all of you. So, looking at the time complexity of this algorithm, here, since you are not making all such comparisons of the pattern when there is a mismatch, right? You are trying to skip good number of comparisons that helps to reduce the time complexity here, right? And another thing that you have taken is from backward rather, right? That was another thing which have been fetched here. So which makes your algorithm in a very worst case scenario to reduce to nm. See, in average case, this complexity was average case of your brute force, yes or no? Big of nm. Sorry, this is the worst case. You probably, sorry, huh? Worst case of your brute force is big of nm, and average we said how much, n plus m we said, right? So, but Barmore, see, worst case time complexity in Barmore is same as that of your brute force, but it is very fast when the alphabet set is large, and it is slow when this alphabet is small. But you can see it significantly faster than brute force for searching English text. If you are going for English text, it is very much helpful and more faster, more efficient than brute force. Okay. I hope it is clear. Now, looking at the worst case of the buyer mode, yeah, looking at the worst case of the buyer, if you have something like as your text, and wherein you have to search for, let us say, ba is a pattern, then what is happening here? The mismatch is happening only at the last. So it means you have to do all these comparisons, like how in even brute force, when you have with the worst case scenario, when you have seen after all the comparisons only you are able to get a mismatch. Similarly, this kind of pattern, if it is given in this text to search for, you can see here you are able to get the mismatch only after you compare all the characters. Fine, since you are doing it from the back, right? So all the characters from the back, they are all equal, right? So only when you reach the first character of the pattern, you get a mismatch. So in order to identify or you encounter with the mismatch, you have to do all the comparisons. So only then you can take a step, right? When a mismatch occur, what is that you're going to do? Last occurrence, it does not fall under case one and case two. Then what do? You say you shift the entire pattern to align p of zero with t of I plus one. This is a I plus one, right? With so that's what exactly here is. You can see here. After you have done the comparison, entire comparison, you got a mismatch here, and it falls under a case three all the time. So in case three, what do? You shift the entire pattern to right to align the p of zero. This is your p of zero, right? With t of I plus one. This is your t of I plus one, right? Again, you start from the last character of your pattern with the corresponding position of your text. But there is a mismatch, but there is a match, and there is a mismatch at the end. So again, you fall under case three, so you will shift the entire pattern to right in order to align p of zero with t of I plus one. That way you do it. So that makes you to do about n m comparisons, right? Which is worst case scenario of your buyer more equivalent to brute force, but then significantly it is better when you are searching it from the alphabet text as we have derived, right? From what we have discussed, right? Now coming to the next algorithm, that is KNUTH Morris Pratt, right? This is another algorithm which is better than I can say brute force. Fine. So if you see in brute force, we were comparing from left to right. Okay, right. In Biomore, we have compared from right to left, whereas in brute force, we have compared from left to right. So same kind of approach that we have adopted for brute force is going to be applied in this KNUTH Pratt KMP algorithm. Fine, it is very similar to brute force as I said, right? But there is a small twist in this algorithm that it shifts the pattern more intelligently than the brute force. In brute force, what happens when there is a mismatch? You will shift the pattern to next of the text. Wherever the mismatch occur in text, Next to that character you will shift your entire pattern by to align your p of 0 to t of I plus 1, right? But then here you will shift the pattern intelligently to align with text so that the number of comparisons can be reduced. So now looking at how does this particular algorithm works. If a mismatch occurs between the text and the pattern, what is the most we can do is basically you avoid the you shift the pattern to avoid the wasteful comparisons. That's what exactly our main answer is. So here, what is the answer for the same is nothing but the largest prefix. What we are trying to do is how we are going to shift this pattern to align with text in order to go for the next iteration for comparison is we are finding out a number with which we can probably increase the positions of both the pattern and the text, and that position the particular constant value how we are going to identify is with the help of this particular mechanism. What is it? The largest prefix of p of 0 to j minus 1, which is equivalent to the suffix of p of 1 to j minus 1. Your pattern from your pattern, what is the largest prefix when your pattern is holding 0 to j minus 1, and the suffix that you derive when your pattern is holding the text from 1 to j minus 1. So identifying the value which is the largest prefix of p of 0 to j minus 1, which is equivalent to the suffix of p of 1 to j minus 1. We'll see here. Let us look at a string. Take a string here, pattern string. For example, you have a pattern string ABAAB. Fine. In this ABAAB, what is the largest prefix which is equivalent to the suffix, largest suffix of this p of 1 to j minus 1? See, while finding the prefix, we are taking the string from 0 to j minus 1, pattern string. But while finding the suffix, we are taking the string of the pattern from 1 to j minus 1. When you take 1 to j minus 1, that is Bob, BAAB. So, what are the largest prefix from this ABAAB? As I said, A, B, A, B, A, B, and name itself A, B, right? And what are the suffixes of this? B, AB, AAB, and name itself Bob. Now, what is the largest prefix which is equivalent to the largest suffix of your this particular string is AB? Yes or no? How many characters it is consisting of? 2 characters. So your J value will be set to 2. Understand? In general, brute force, what happens? Your J value always starts with 0. Your J value always starts with 0 for every iteration. But here we are not starting our J. J is positioning the pattern. So we are not starting our J with 0. Instead, we are taking a value that is coming from this, where what is that this value are coming you are taking it from the largest prefix of p of 0 to j minus 1, which is equivalent to the largest suffix of p of 1 to j minus 1. When you take this particular string above and bob, then you are able to find AB as the largest prefix of p of 0 to j minus 1, which is equivalent to the largest suffix of p of 1 to j minus 1, carrying how many characters? 2 characters, right? So this 2 will be your j here instead of 0. It means you are able to rescue how many comparisons? 2 comparisons. That way you are intelligibly rescuing the comparisons from in the further iterations to reduce the time complexity of the brute force algorithm. Fine. So this is the main concept behind KNUTH Morris Pratt. This is one of the algorithm which helps you to reduce the time complexity to uh, very much further as you can compare with the brute force algorithm, right? So, but then here, what is that you do is you are pre-processing your pattern itself, right? Yeah, there are two strings you have. You have a text and you have a pattern string, right? So you are pre-processing your pattern and then identifying the failure function value. So, like for example, if you have a pattern like this, ababa, a b a b a, right? So you need to first calculate the failure function value, which will be set to j, which will be this failure function value is nothing but what, the largest prefix of your p of 0 to j minus 1, wherever there is a mismatch. When you start comparing your pattern with the text, wherever there is a mismatch, the mismatch value of j is nothing but in pattern rather, right? So mismatch value of j will be taken as from 0 till j, that your pattern will be taken in. From that particular pattern you try to identify the failure function value. This failure function value will be given as your j value instead 0 rather, right? So how you are going to calculate the failure function value is with the help of this particular technique that I have discussed, right? Largest prefix of the p of 0 to j minus 1, which is largest suffix of your p of 1 to j minus 1. Okay. So when you take this particular pattern ababa, right? So from this pattern, now if you have to calculate the failure function values when your mismatch occurs at 0, at 1, at 2, at 3, at 4, at 5. How many characters you have? 1, 2, 3, 4, 5, 6. So at 0, 1, 2, 3, 4. Basically, the last is not required anyway. So we will take till up to n minus 1. We will take up to j minus 1, right? So it means 0, 1, 2, 3, 4. Till 4 will take, right? Now, failure function value for 0 anyway, it will be 0, right? For 1, because you don't have any characters before it rather, right? For 1 also it is 0 itself, right? Because you take it till 1 less than the character, right? If your string carrying only 2 character, 1 less than it is nothing but only 1 character left. So what is the index position of that character is going to be 0. So for 0 and 1 it's going to be anyway 0 itself. From 2 you can see, like for example you have ABA, right? ABA. So in this, how do you calculate? I'll show you how do you calculate this failure function value, and we have calculated to 1 here. So this is your string to identify the prefix, right? P of 0 to this is 0 1 2, right? 0 to 2. And when you are identifying the suffix, for suffix, what is your string that you take from 1, from 1 till j minus 1, 1 to 2? It means BA, right? So when you are finding the largest prefix, you'll be finding it from aba. But when you are finding the suffix, you'll be finding it from ba. Understand? So what is the largest prefix of aba? As you know, the name itself, that ABA itself are A, are AB. Yes or no? And what are the suffixes that you get from BA itself and then A? So in these two sets, which set is equal, which element is equal? A is equal, right? What is the largest prefix of this particular set equivalent to the largest suffix of this particular set? Which is nothing but A. Fine. A means it's going to be 1, right? What is how many character that it is carrying? 1. So the value will be 1, like this. Okay. Similarly for 3 also, when you are calculating, how do you calculate for 3? That is ABAA. From this, you are going to find the prefixes, and from BAA, you will find the suffixes. So from A bar, if you find the prefixes, you'll get A bar itself, and then you get A bar, or you get AB, or you get A, right? And from this bar, what do you get? You will get the name itself, of course, right? and then you get AA, then you get A. So in this two sets, identifying the elements which are equal, this is only one, right? Which is A. Having how many characters? Only one character. So this is the failure function value will be. The failure function value will be one here, rather, right? So similarly for four, which I have already calculated here, you can see which you have got as two. So this is how we are going to calculate the failure function values for our pattern. It means you are pre-processing the pattern itself, right? In order to locate j instead of 0, fine, with certain higher value, so that comparisons can be rescued from doing in the next iteration, the subsequent iterations, right? That's how the algorithm is here, constructed. You can see here. The compute fail function is a function which is calculating the failure function value here, right? When there is a match, it's fine. So when there is a mismatch, you will be taking from the fail of j minus 1 to j. So otherwise, fail of I equal to 0, right? Initially, your fail function is with zeros, and then it's going to be updated based on this particular algorithm, and the same kind of algorithm is repeated for KMP match as well. You just trace this algorithm for the given text and then pattern, and take this example, and we'll probably trace the same here and see how our algorithm works here. So this is your text given, and this is your pattern given. So now, when you're comparing the characters of a pattern with a text, very similar to the brute force, you start with the first character of your pattern and with the first character of your text, right? Let us say I am taking to position the text, and J am taking to position the pattern. So there is a match, then you advance. It means you increment I and J. There is a match, so you increment both I and J, right? There is a match, increment both, right? There is a match, increment. There is a match, you increment. Now there is a mismatch. You can see when there is a mismatch here, what is that you do here is your j value is what? Your j value is 6. So you will find the failure. You reduce this j value, that is your k will be j minus 1, right? you take the you take the decrement of this j value as k, and you pass this k to failure function to get the value to set j here. Okay, so what is 5 failure of 5 failure? Sorry, this is 0 now. Index is 0, 1, 2, 3, 4, and 5. So j value was 5, not 6. Okay, j value was 5 here. So your k value will be what? As per j minus 1, if you calculate, k value becomes what? 4. So what is a failure of 4? Failure of 4 is 1. So your j value starts with 1 instead of 0. So you can see here j is starting with 1 here, and I is there itself, right? I is there itself, right? So you start comparing with, you can see before this character, that was already, you can see without matching, it was matched itself. That's how intelligible shifting we are doing in order to rescue certain comparisons which we know that they are anyway going to be get matched on, right? Is a kind of knowledge based techniques here we are probably applying in order to avoid such kind of comparison. You can see here when j is set to 1 and aligned with t, before character is already matched. Yes or no? And now you will move further. Fine. Next character, when you see there is a mismatch. Yes or no? You got a mismatch. When there is a mismatch, what is j value here? J value 0, 1, 2. This is a j value. J value is 2. So what will be the k value? K is your j minus 1. Is nothing but 1. So what is the failure function of 1? That is nothing but 0. It means j has to start with 0. You can see here j is starting with 0 here, right? Fine. So again, you compare it from I is not moved because there is a mismatch occurred at text. So you don't increase that position rather, right, until there is a match comes from the pattern. Okay, so you can see here I is there itself, it is written there itself. Then again you start comparing this j positioned pattern character, which is nothing but a. So there is a match, and there is a match, and there is a match here, and there is a match here, and there is a mismatch here. So I is somewhere here now, right, and j is here. Understand? And what is j value? 0, 1, 2, 3, 4. Now what will be k? K will be 3. And what is failure function of 3 is nothing but 0. It means j start with 0 again. You can see I is there itself, and j is starting here. There is a mismatch again. Then what happens? You again start with, when there is a mismatch, what do you do? And failure function value when it does not get you, then both are going to be incremented rather, right? You can see here I will be incremented and j will also be incremented, right? You can see j is incremented and I is incremented. Fine. And then you start comparing the characters of pattern in correspondence to the text. You found there is a match, there is a match. So when there is a match, both are advancing, right? I and j both are advancing here, and you got match at the last character as well. So I was here and j was here, and when both are advanced, and you got the last character of the pattern get matched with the corresponding character of the text, then what do? You will return the position of the text from where actually that particular pattern is found, right? This is what exactly we do it in uh, KMP algorithm, right? So I hope you understand. If you look at the time complexity, it is m plus n, right? This is the average case of your uh, you know brute force, right? So the optimal time of KMP is m plus n. The disadvantages associated with this, it doesn't work so well as the size of the alphabet when increases rather, right? And there's a more chances of mismatch when there are alphabet set is increased. That mismatch tends to occur early in the pattern, but KMP is faster when the mismatches occurs later. If the mismatches occur later, then it is good. It is faster. I hope this is clear to all of you. Yes. Please trace the algorithm with the no text and patterns given there for practice.